Hi, I'm Brendan Sauer, Product Manager here at Discover Battery for the Advanced Energy Systems Division. Today in front of you, we've got two 48-volt batteries, lithium batteries that is, and right here, very well-known 48-volt block in the renewable energy and energy storage industry. 3.5 kilowatt hours this module, only acts as a lead acid replacement, so no communications. It can't report state of charge or any other parameters to inverters. And on the other side, Discover's very own 4248-6650. This one can both act as a lead acid replacement, or you can take advantage of the smart BMS and its reporting capabilities. So without further ado, let's pop the tops off, let's look inside and start comparing design philosophy. Okay, so we've got this cell block out of the case. Quickly, I want to mention I'm wearing gloves. That's actually because this cell block is incredibly sharp. Be careful. I don't recommend you do this at home. Also, we've gone and taped off any of our loose ends here, just so we're not shorting anything out, and I've also disconnected the BMS. So with that all done, let's get into the detail. So we've got tab welded cell modules, fairly common. Also on either side of the pack, this is how they make the series connection. So they go ahead and they'll tab weld these tabs together to make that series connection. You can see a lot of wiring here. So they've gone ahead and soldered on their voltage pickups here. There's no mechanical connections. Also, I noticed that we've only got voltage pickups. There's no temperature probes anywhere in this cell block. Also, draw your attention to this mechanical tape, if you can call it that. So, just some simple tape with maybe nylon straps inside. Lots of hot glue, and really there's no mechanical support. So even if I push just a little bit, it's kind of hard to show, you'll see that I can get this cell block to flex. Let's take a bit of a deeper dive into the electrical. So right off the bat, I see this Arctic Ultraflex cable, absolutely beautiful stuff, love seeing it. And the way they attach the cable to their bus bar, you'll see they've removed a section of the insulator and just gone ahead and soldered this right onto that tab. Also, I've got a breaker in my hand. We're going to talk a little bit further about why I think this is here when we look at the BMS. Let's go ahead and pull this BMS subassembly off and take a look. Okay, so let's go ahead and pull this honeycomb material off. I think that's just there as a mechanical structure to hold everything together. And what we're left with is a fairly typical solid state relay made of MOSFETs, some passive balancing, and I'll go ahead and point out this is the only temperature sensor I can find in the pack. So we're not actually monitoring cell temperature here, we're only monitoring heat sink temperature on the relay. What you see before you is two 12-volt lithium batteries. I call them SLA retrofits. I went ahead and tore one down a while ago, and you'll notice a similarity in construction and cell wrapping. So same cells, same BMS, same methodology here. That's where I went ahead and found this BMS. So it's actually the same board, just a 12-volt version. Looking closer at the BMS, if I take the heat sink and put them side by side, you'll see that they're of the same flavor. So that's the cue that they're a similar BMS. Here we've got 4 channels of passive balancing. This is from a 12-volt battery. So if it was on a 48-volt battery, you'd see all 16 channels populated. Over here we've got the solid state relay, so the charge and discharge bank of MOSFETs. There's no energy absorption devices around this bank, so if there was ever a large inductive load, characteristic of a large DC motor or something, and you tried to interrupt that at high current, likely we'd see a few MOSFETs fail short. And finally, back to the DC breaker, after reviewing the solid state relay and determining that there may be some susceptibility to large inductive loads and high current, that's why I see the breaker. So let's go ahead and rely on this as opposed to the solid state relay for high current interrupts. And in conclusion, that's about it. So when you see a lead acid replacement lithium battery, these are the components that you will usually find. And moving on, the 4248-6650, this is Discover Batteries, the largest 48-volt lithium battery. Gone ahead and popped it out of the case. What's left is the cell block with the electronics package on top. And really quickly, focusing on the cell block, you can see that the cells are actually attached in series here as well as parallel. So the current flow is actually going through the cell, whereas alternatively, it's quite common to have just the modules paralleled with a nickel sheet, and that current flow is kind of wrapping around the cell modules. So here you see it going directly through. Also, you'll notice some mechanical structures throughout the battery. These came from a lot of learnings in certifications. So UN 383, UL 1973, and 2271. In order to tie this cell block to the case and really couple a tight mass, as opposed to if the cell block was just floating inside the case, you'll get two masses moving at different frequencies. We've got this structure here to hold it all together so we don't shake apart when you go to shake and bake this battery during certification testing. Also in the end, you'll notice very large plate here. So we're not using thin nickel material. Helps us carry a lot more current, a lot more power, and adds a bit of robustness. So here, you can't quite see it, but inside the cell block, there's an array of temperature sensors. They're also on the solid state relay and the BMS. So that allows the BMS itself to paint a pretty robust picture of what the thermal profile is at any given time. Also, you'll notice that there's no wiring harnesses here at all. We totally designed that out. So voltage, current, temperature pickups and sensors, there's no wiring harness for that anymore. The actual main current path doesn't go through any cables. It's all through bus bar, 72 millimeter squared bar. And essentially what we're left with is the BMS package. Now this I can actually pull right off the cell block and transplant to any voltage variation that we have. All right, so the BMS on this battery is actually composed of two boards. We have the solid state relay and then the main digital board. If I pull off the solid state relay, well, you'll see a lot more bus bar. So that we're carrying current through the bar as opposed to just the copper on the PCB. Here are a few more comparables. So a pretty standard solid state relay and BMS out of a straight lead acid replacement. So just a few more examples for you. Heat sinks over here, typically not very fancy, no fins, just flat metal bar. Once again, not a whole lot of copper, not a whole lot of material for current to flow through. And finally, just one more that I've got. So typically a lot of the same construction you see, but there's definitely a big difference between the two. Also, you notice that we are internally fused, so just one more protective measure, just in case something goes wrong and you really short circuit a load. All right, let's move on to the BMS. So the BMS here is our opportunity to be more than just a lead acid replacement. So once again, you can use these batteries as just a lead acid replacement, or you can take advantage of all the communications and further features that this board here offers. So we do have our passive balancing, voltage monitoring, current and what have you all here. But this board is what allows us to offer further features and really have an advanced energy solution and not just a lead acid replacement. So what we've accomplished today is a teardown of two lithium batteries, each with their own design philosophy. We've taken a deep dive into electronics. So we've got the simple lead acid replacement BMSs that have no digital functions, so they're not going to be relaying state of charge, talking to you, versus a BMS that can act as a lead acid replacement, but also has the ability to have external communications, data logging, state of charge communication, or even control of inverters and chargers. Also, we've taken a bit of a further look at the cell blocks, so different current flows, materials, mechanical integrity, and I hope you can now walk away with a little bit of a deeper understanding of two different philosophies as it applies to building lithium-ion batteries.